Welcome. Let's get started. Course announcements. First of all, a reminder that everyone should be thinking about collaboration on the problem set. Discuss the problems with other people. If you want to find somebody to discuss with, come to office hours because there are often a lot of people looking to discuss problems there, but also post in the Slack and say, I want to discuss this problem. If you haven't already done that, I really do encourage you to do that. Math and problem solving and just science in general should be collaborative. About problem 4, don't stress the proofs. The goal is mostly to work out if things are true. This is the one, the problem with, is this true? Is it not true? If it's true, the proof should be pretty quick. It should be just like one line. Don't really worry about whether it's a super formal proof. These things are sufficiently simple that it's sort of not clear exactly what a full proof is. The important thing is to work out if something's true or not, and if it's not, work out a counterexample. And this is just a really good way to think about math in general or science or problem solving. First, try to convince yourself that something might not be true, or see if you can do that. See if you can find a counterexample. So this is sort of trying to demonstrate that kind of thing. Problem 3, I realized it would just be a bit more algebra than was necessary. So feel free if you want just to set A equal to the identity matrix so that you're just looking at xbx, so the trace of xbx. You can do the full thing. This is just a special case of that. But feel free to just set A equal to the identity matrix, just to make it a bit less thorny algebra, and no need to do that. A clarification. During class, there was really no need for you to read other chat responses. I realized that people might be feeling sort of overwhelmed by the amount of information coming at you. The things you should be paying attention to are the slides and ideally things that I'm saying. That would be good. But I realize when lots of people are posting responses in the chat, there's no need for you to read other responses. Feel free to, but I will try to say out loud things that I think are important. So the chat contributes to the participation grade. So you should participate in the chat, but do not feel a need to read the things that other people are posting in the chat. I will say what things you should be reading. Like if there's something important in the chat, somebody makes a really cool suggestion, I will be summarizing that and saying that out loud. So everyone should be posting in the chat because that's how part of participation, and that's part of having a sort of discursive atmosphere. Feel free to read what other people post, but you don't feel a need to. I will say things. Does that make sense? Anything that people have questions about? How is participation graded? Participation is graded, well, so there's attendance, which is did you appear or not? And there is participation, did you contribute to the chat? It's not based upon like right answers. It's based upon making a meaningful effort. So if you post in the chat like just smiley faces, that is not contributing to participation. But if you are trying to answer questions, then that counts. Smiley faces are fine. They're just not part of the participation. Okay. Any more questions? Okay. What if the question involves smiley faces? No comment. Okay, well, let's get going. This is probability number 2. And there will be a probability number 3 as well. So first, a review of expected value. Expected value, if you have a discrete valued random variable, is the sum for all possible values of that random variable of the probability of getting that value times the value itself. So it's just a weighted average. It is literally just the average that you're getting if you were to sample a bunch. If you take some people in from the real world, you measure their heights, the expected value of heights is just the average that you would expect to get if you took a really large number of people. It converges to the expected value. We saw that the expected value of the sum of two things is just the sum of the expected values, and that is always the case, regardless of what the random variables are. That's called linearity of expectation. That is really important. So expected values add. Expected values don't generally multiply. They multiply if the variables, the random variables involved, are independent. Okay. Any questions from last time? Okay. So now let's look at variance. Variance is basically, it comes about because expected values don't multiply. So generally, the expected value of x squared is not equal to the expected value of x squared. Sorry, I forgot to make these special e's. That's math BBE in LaTeX. You can take a look at the source code for the lecture if you're curious. The variance of a random variable is just defined as the difference between these two expected values. So it's the difference between the expected value of x squared and the square of the expected value of x. I know this is hard to say. This is one definition of the variance. You will see other definitions of the variance as well. An alternate definition of the variance is that it is the expected value of the square of x minus expected value of x. So it is, if you imagine expected value of x is the average of x is just a constant. So if you look at how far away x is on average from its average, I know that's a bit weird, but it is like the square of how far away x is from its average. Now, why are these two the same thing? Yes, you can derive the alternate definition from the first definition. So let's just do that right now. This, if you just expand out what this square is, it's expected value of x squared minus 2x times expected value of x plus expected value of x squared. Again, you should think of expected value of x as just a constant. So for example, the mean of x might be like 1, in which case it would be x squared minus 2x plus 1. Now, how can we deal with this? What can we do with this? Great, linearity of expectation. We have the expected value of a sum, so we can just turn it into the sums of the expectations, or in this case, it's a negative sign too. We know that constants just come out. So expected value of x squared minus 2 expected value of x times, it's a little bit awkward. But this can actually be a lot simpler. Why? How can this be made simpler? The expected value of x is just a constant. So we can treat that like a constant too and move it out. So this just becomes 2 times the expected value of x, moving out this expected value, times the expected value of x. And this is just expectation of expectation is, since this is a constant, the expectation of a constant is just the constant itself. Expected value of x is not a random variable. There are no probabilities associated with it. So we have this. And then if you just realize that these are just the same thing, you end up with the original definition. Are there any questions? So this second definition is why the variance is always non-negative, because it's the expected value of something which is always non-negative. That's why you can do something like, say, standard deviation is the square root of variance. You wouldn't want to do that if variance could be negative. Okay. What is the variance of the number of heads in a single coin flip? Suppose it's a fair coin flip, half heads, half probability tails. It could be heads, it could be tails. Remember that the average number of heads, the expected number of heads, was 1/2. There's a lot of disagreement here. Let's go through the definition. So we want to find, again, this, the expected value of x squared minus expected value of x squared. If x is the number of heads. So we know that the expected value of x squared is, there's a half probability that's 0 squared. There's a half probability that's 1 squared. So that's just 1/2. But then there's the second term. And we already knew that from last time that expected value of x is just 1/2. So the variance is going to be 1/2 minus 1/2 squared, which is just 1/4. And in general, when are we going to have the variance be 0? We're going to have the, I'm not going to prove it here, but we're going to have the, actually, yeah. I will, if I have time at the end of class, I'll give you a sense of why that's true. But the variance is going to be 0 when the random variable is not random. It's always equal to the mean. So in general, if you have a random variable, it's actually varying, then you have the variance being positive, strictly positive. Okay. And there was a question about expected value of x squared being greater than being not equal to expected value of x squared if x is not unless x is independent of x. X is never independent of x. Basically, but yeah, if there's no if there's no variability in what the random variable is, then it is essentially independent of itself, because you don't gain any new information by knowing what x is, because you already knew what x was. So that's an intuition for it. Yeah. Okay. What is the variance of c times x? If you multiply your random variable by c, how does that change the variance? Maybe if you're changing units, the variance of heights, you wanted to change from inches to centimeters, so you're multiplying by a number. We knew that the expected value of cx is c times the expected value. Yeah, so you have to be careful. It's not c times variance of x. If you look at each of these terms, you see that we get a c squared from the first one and a c squared from the second one. So we just get the variance of cx is c squared times the variance of x. Okay. This is one of the reasons why people think about standard deviation. Because standard deviation scales linearly with the thing you're in there. So it has sort of the same units as x. Variance doesn't have the same units, as x. And if you're measuring something in inches, then the variance is going to be in square inches, whereas the standard deviation has units of inches. And this is the standard deviation of Cx is just C times the standard deviation of x. Okay. Do we have linearity of variance? Do we ever have linearity of variance? So we do if the events are independent. If these random variables, if they are independent random variables. In general, no, we don't. So why is this the case? Let's just write it out. Variance of x plus y is equal to expected value of x plus y squared minus expected value of x plus y squared. That is equal to the expected value of x, just expanding this out, minus the expected value of turning this, doing linearity of expectation here. And let's expand all of that and get something really thorny here. But if you look here, and here I'm just doing linearity of expectation over here too. Now we can group these terms. We can be like, oh, this one sort of looks like this. This one sort of looks like this. This one sort of looks like this. So if we group them like that, then what do we see? Yeah, so we get variance of x, first term, variance of y, second term, plus, and then this 2 times this difference. And this difference we know was 0 if they are independent. So there we go. That means that the variance is sum if they are independent. If they are independent. Okay. This is particularly important. Often you think of, if you have 2 independent Gaussian distributed variables. We'll talk about Gaussians next time. But then the variance is sum, but that's if they're independent. As an indication of why, I think that's enough. Oh, why are we using square brackets instead of parentheses for variance and expectation? That's a really good question. It's sort of convention. I don't know that there is a good reason for it, but that's just what people will often do. Yeah, I'm sorry. It's not very satisfying. What is the variance of the number of heads for n fair coin flips? I would not use curly braces personally because curly braces are generally used for sets. Just for what it's worth. But I mean, I know that there are different conventions for these things. What's the variance? If you flip a fair coin, fair is just 1/2 heads, 1/2 tails. What's the variance? How would we do this? So we could, one way we could do it would be to literally calculate the expected value of number of heads squared, which would be like the probability of getting 5 heads times the number of ways to get 5 heads. So it's to be like 5 squared times n choose 5 plus 4 squared times n choose 4 plus 3 squared times n choose 3 plus 2 squared times n choose 2. Summing all of those things, also going all the way up to n squared times n choose n. That would be an answer, but it would be a little bit tough to compute. You need to use a combinatorial identity to work out what that thing is, but there's a simpler way. We can just let x be the total number of heads and let xk be the number of heads in the kth flip. And as people are suggesting, since each coin flip is independent of the others, we have this independent thing. So in this case, variance of x is the sum of the individual variances of all the specific xk's. And so since each variance is 1/4, we know that the overall variance is n/4. Is 1/4 because we computed it before. Okay, so the standard deviation of this, the square root of the variance, is root n/2. And you can think of standard deviation as sort of like roughly how much you might expect that the variable is going to vary. This is not exactly the case, and it requires you to have, for example, a Gaussian variable. But if you had a nice Gaussian variable, and this is actually very Gaussian, as n goes to infinity, we'll see that this actually is exactly the definition of the Gaussian. But the standard deviation, it should be like how much you expect it to vary around the mean. So it's not formally, it's not exactly how much you expect it to vary around the mean, but it's like sort of ish it's going to vary around the mean, and that is root n/2. So if you have like n/2 being the mean number of heads, the expected number of heads, you see that the amount that it varies grows as square root of n, which is sort of important in that you have something that's tightly concentrated around n/2. As n gets big, you're never going to have n/4 heads. That's very unlikely. You're going to get n/2 sort of plus or minus root n/2. Does that make sense? Okay. If you're actually looking for the expected deviation from the mean, that's not expectation of x minus mean squared, it's expectation of x minus mean absolute value, and that's actually different from the variance or from the standard deviation. But we're not going to get into that. And for a normally distributed variable, these two are somewhat similar. Okay, that was just some intuition. Conditional probability. So P of A line B, it's read as P of A given B, is the probability that event A occurs given that event B occurs. Formally, what this is probability of A given B is the probability that both A and B occur divided by the probability that B occurs. And here's a way to see why that makes sense. If you just multiply out, the probability that both A and B occur should be, you can imagine sort of choosing B first and saying, okay, what's the probability of B? And now suppose that I already know that B occurs. So probability of B, what's the probability of A given that I know already that B occurs? So that's why you should think of probability of A given B like this, because probability of A given B times probability of B is just probability of both A and B. Questions about that? What exactly does occur mean? Yeah, great question. So an event could be, it rains today. The probability of it raining, given that it is cloudy, is the probability that it is both raining and cloudy, divided by the probability that it is cloudy. Or alternatively, the probability that it rains and is cloudy, the second equation is the probability that it rains and is cloudy is the same as the probability that it's cloudy times the probability that given that it is cloudy, it also rains. But you can also think of an event as being a as being to do with random variables. More you can define a random variable such that the random variable is 0 if it doesn't rain and 1 if it does rain, or you can just think of an event might be the probability that the number of heads is exactly 4. That is an example of one event. So, yeah. Event is just something that can happen. It either happens or it doesn't. There's a question about Bayes' theorem. We'll get to that in a moment. And yes. So the question is this is understanding probability intuitively, how to talk about it formally. Unfortunately, the way to talk about probability formally does involve things like measure theory. This is as formal as we need to be. But you could think of it with truth tables, for example. You could think of an event as being assigned, every event as having either true or false. What is the probability of A given A? Great. So intuitively, it should be 1, because we already know A is occurring. Probability, and let's just write it out. The probability of A and A occurring is just the probability of A. So if we plug that in here, we get probability of A over probability of A is 1. Great. Cool. So here's an example. Suppose A is the event of getting all heads on 3 flips of a fair coin, and B is the event of getting heads on the first flip. Then what is P of A given B? And you just write this out, or sorry, intuitively, once we've already decided on the first flip, there's a 1/4 probability that the other 2 are heads. And if we want to do this formally, we just plug it in here. Probability of A and B is just the probability. So A is all 3 flips are heads. B is first flip is heads. So the intersection of the 2 is just A itself, which is all 3 flips are heads. So 1/8 probability of A and B. 1/2 probability of B, so 1/8 over 1/2 is 1/4. This is just formalizing what our intuition was. What about if B is getting tails on the first flip? What's P of A given B? Exactly, it's just 0, because P of A and B is just 0. So P of A given B is 0. Cool. Now let bar A be the event that A doesn't occur, or not A. As a warm-up, what's P of A plus P of not A? A either has to occur or not, so this sum is just 1. What is the probability of A and B, or A and not B? Great. B either occurs or doesn't, so probability of A and B plus probability of A and not B is just probability of A. What is the probability of A given B plus the probability of A given not B? Careful, everyone. It's a trap. So let's write this out. This is why it's really useful sometimes to formalize things, especially when you have A given B. It's a really good idea to write out formally what A given B is. So let's write this out. This is not always equal to P of A. Probability of A given B plus probability of A given not B is probability of A and B over probability of B plus probability of A and not B over probability of not B. Cool. So you can simplify this thing as 1 minus probability of B, but what we'd really like, we notice these two numerators are going to sum to P of A. Okay. But we don't know anything about these denominators. They're not even the same. So what we know is if we multiply this first one by P of B, if we multiply the second one by 1 minus P of B, then we would get P of A. And the numerator is add to P of A. So if you multiply it out by the denominators, you'll get P of A. But in fact, you can really almost never get that this is equal to P of A, because you have to multiply by these things which are both, or at least one of them is less than 1. Strictly less than 1. They're both at most 1. So basically, you're never going to get that this sum is equal to P of A. There's a question about whether this sum is equal to 1. It's also not equal to 1. And sort of intuitively, why is this not equal to P of A? Well, because you need the probability of A given B. So suppose that you're looking at the probability that the probability that I win the lottery, given that somebody from the lottery board. So suppose that A is I've won the lottery, and B is somebody from the lottery board calls me up to say I have won the lottery. So probability of A given B is probably pretty high. Like if somebody from the lottery board actually calls me up and says I won the lottery, then I assume that this is a very high probability. Probability of A given not B, probability that I've won the lottery given that nobody calls me up is definitely much smaller, because I'm very unlikely to win the lottery, especially since I actually am not participating in any lotteries. But if you just look at the sum, well, the sum is going to be very large because this term is actually pretty large. Yes, of course, it might be a fraud, but if they actually are from the lottery board, probability of A given B is pretty large. So you definitely don't want to say, oh, well, obviously probability of A is really large because the probability that B happens is very small. So that's why you need to multiply by P of B and 1 minus P of B to get this. If you didn't get that, I realize I didn't write it down on the slide. But yeah, so you need to sort of weight by the probability of what you're conditioning on. Are there any questions? And yes, it is always less than or equal to P of A. Oh, sorry, no, it's not less than or equal to, it's greater than or equal to P of A. Because these things are less than or equal to 1. Okay, so beware of things that look like they might be true with conditional probabilities. It's always good to just write out the scenarios and try to disprove it to yourself. Okay, somebody brought up Bayes' theorem. Bayes' theorem is one of the very simplest theorems to prove. We will just prove it in like one line. Since P of A given B is defined as P of A and B divided by P of B, if you just, another way to write it is this, but you could do the same thing of P of B given A. Given that it is cloudy, what's the probability? Sorry, given that it rained today, what's the probability that it was cloudy? So that's another thing you could think about. And same definition of probability of B given A. So probability of B given A times probability of A is just, again, equal to probability of B and A both happening. Since these two things are the same, you can just write that probability of A given B times probability of B is equal to probability of B given A times probability of A. And then this is the way that you generally see Bayes' theorem written down. A given B, P of A given B is equal to P of B given A times P of A over P of B. That's just literally the same thing as this. So this is basically just the definition of conditional probability. That's what Bayes' theorem is. No magic here. Questions? So this is really fundamental. There's a whole area of stats which is based on Bayesian approaches to things. And regardless of whether you're a Bayesian or frequentist, clearly Bayes' theorem is true. Some questions. Is it true that P of A given B equals P of B given A? Nope. Why? Again, it's probably a good idea when you're thinking about such things to just write down some stuff. I'm just going to write down Bayes' theorem. We can write down Bayes' theorem here. And yeah, it's going to be the case if and only if, actually, P of A equals P of B. So this thing would have to be equal to 1. Okay. Cool. What about probability of A given B? Is it equal to the inverse of probability of B given A? I mean, these kind of look like divided by. So is it true that A given B is equal to 1 over B given A? Darn, that is also not true. So the second is, in general, actually greater than 1. So it's not a probability at all. So that 1 over probability is definitely not equal, cannot be equal to a probability, unless both probabilities are 1. Okay. So let's now go to the problem that was stated at the start of class. A test for a disease is 90% accurate, both for positives and negatives, meaning that 90% of the time, a person with a disease tests positive, and 90% of the time, a person without the disease tests negative. 1% of the population has the disease. What is the chance that a randomly selected person who tests positive actually has the disease? These numbers are not related to the numbers for COVID-19. Okay, so let's work this out. Let A be the event that the person has the disease. B be the event that the person tests positive. What do we need to work out? I want to find P of A given B. Great. How do we write down some of the things that we know? The condition that 90% of the time a person with a disease tests positive. What is that condition? Like, how can we write it down? Is there a simple way to write it down? It's always good to write down the things we are given. Okay, if a person has the disease, that's A, and given that they have the disease, the chance that they test positive is 90%, so 0.9. Probability of B given A is 0.9. Okay. So by Bayes' theorem, we would have this. That means we need to work some things out. What is P of A? Probability that the person has the disease. Prior probability, if you like to refer to it as such. So yes, that is just 0.01. We're told that 1% of people have the disease. What about P of B? Are we given P of B? That's the chance that a person tests positive, a randomly selected person. So we want P of A given B, but in order to get that, we're probably going to have to plug in P of B here. How do we get P of B? Yeah, we can divide into two cases. Probability of B, this is probability of B given A times probability of A, plus probability of B given not A times probability of not A. This is basically just writing it as, this first term is B and A, this second term is B and not A. So that's the probability, going back into words, that's probability that you test positive given that you do have the disease, times the probability that you do have the disease. Remember, this is important to add here. Plus probability that you don't have the disease, times probability, that you test positive given that you don't have the disease, times the probability that you don't have the disease. Okay, so let's work out what this is. We already knew that P of A is 0.01 and P of B given A is 0.9. What is P of not A? Just 1 minus 0.01, so 0.99. Great. What is B, probability of B given not A? We're given that probability of not B, testing negative, given that you don't have the disease, is 0.9. So probability of B given not A is 1 minus 0.9 is equal to 0.1. That means that if you wanted to calculate P of B, you just plug all these numbers in, and you get 0.108. Okay, let's go back to Bayes' theorem. We had that probability of A given B is equal to the probability of B given A times probability of A over probability of B. So plugging in our numbers, we get about an 8% chance that if you test positive, you actually have the disease. Let's interpret this. So if you have a pretty accurate but not very accurate test, and a very small fraction of the population actually has the disease, then if you tested a random person, it would be more likely, vastly more likely, that it was a false positive if it came up positive than that it was a true positive, just because the prior probability of that person having disease is very low. So reasons why this doesn't doom us all. First, real tests are more accurate than this generally. For example, PCR for COVID-19, for the coronavirus that causes COVID-19. is very accurate. And also that randomly tested people are not typically what you're actually doing. Typically, people are being tested if they have if there's some reason to expect that they might have the disease. So it's you are changing a couple of these probabilities in real life. So that is actually all that I wrote slides for. We have 5 additional minutes. So I'll first take questions, and then I thought that I could, it's never happened before, I thought that I could just do something cool on the whiteboard with linearity of expectation called Buffon's needle. Any questions? Okay. Great. So let me share my screen again here. Can you see my whiteboard? Great. Okay, so Buffon's needle. This is a fun math puzzle. Suppose that you have some equally spaced lines on a piece of paper, and they go off to infinity. And suppose that, and let me try to remember exactly what the values are here. Give me one moment. I didn't prepare this, so I'm just doing this from memory here. Ah, yes. Okay. So let's say that the distance between these lines what is it? One moment. Just reminding myself of one variable here. Yeah. Okay, so let us assume that you have the distance between these lines be A. So there's some distance between the lines A. It's all the same for all of these lines. Okay. And you're going to throw down a needle, and the needle is of length B. And the needle can be thrown with any orientation. It could cross multiple lines. It could cross no lines. Let's assume, furthermore, that we actually make B be less than, sorry, I drew this badly. Let's make B be less than A. So that B is less than A, so that it never crosses more than 1. It either crosses 0 of these lines or it crosses 1. Okay. Now, what is the probability that the needle crosses a line? It's very hard to draw on this whiteboard. So this has a really, really beautiful answer, and let's work it out. Feel free to go at any point if you want. This is just completely for fun. So let us work out this by linearity of expectation. Suppose that you have this line, and you add another line here. You have two lines of any length. What is the probability that the total bent line is going to let's change this problem a little bit. Let's make it be the expected number of crossings, okay, for a line of length b. Now, what we can work out is we can think about number of crossings for a bent line with lengths b1 and b2. Okay. Now, clearly, by linearity of expectation, we can just think about both of those lines individually. Number of crossings for b1 plus the expected number of crossings for a line b2. Now, what this is saying is that, if you extend this logic, if you have a bent line, it's just proportional to the length of the line. There's like some constant, c, times the length of the line. The total length, right? Because if you split the line in two, then you're going to get the expected value for one half and the other half. And now here's the magical part. Suppose that your line is actually bent so much that it looks like a circle. Okay. And suppose that you pick your circle so that it is exactly this size. So the radius of the circle is a. And I'll come back to the question in a moment. If you throw this circle at this board, it's going to intersect exactly twice, because it's never going to be exactly like this. It's always going to be like, it's going to go, sorry, that was terrible. It's going to go over two of these lines, no matter how you throw it. So the expected number of crossings for a circle of radius a is 2, because it's always 2. Now, here's the really cool part. We knew that a bent line, the expected number of crossings is proportional to the total length of the line. What if our bent line is very close to this circle? It's like bent so many times that it goes around all the circle. That has to also be 2. And that means that 2 is equal to c times the length of this bent line. And what's the length of the line? Well, it's the circumference of a circle of radius a, which is 2 pi a. So that means that 2 equals c times 2 pi a. And so c is equal to 1 over pi a. So what happens if you take a line of length b less than a, or just a expected number of crossings of a line of length b? Well, you get c times the length of the line, which is bc, which is b over pi a. So for example, if b is equal to a over 2, then you get 2 over pi. What is it? 1 over 2 pi. So this is basically saying, if you throw enough needles at equally spaced lines, you can work out the value of pi, because the chances that a needle intersects a line are going to be 1 over 2 pi, if the needle is 1/2 the distance between the lines. And this has actually been used to work out the value of pi. It's not a very good way to work out the value of pi, but it is a way to work out the value of pi. This is called Buffon's noodle. It is making, this proof is called Buffon's noodle. It is bending the needle into a noodle. Okay, so that is a cool, somewhat silly application of linearity of expectation. Have a good weekend, everyone, and good luck with the problem set.